So we're going to change gears a little bit. This is very much now focused on academia, or at least focused on people who train people kind of talk. Because just out of curiosity, who here has had to teach someone else how to design a device before? Who here has been like, man, I wish there was a textbook? Yeah. I've been doing this for a little while now on the teaching side, and I need to start with some disclaimers. I wasn't a particularly great student at these things, which I think is sometimes helpful when teaching, but I'm also trying to teach this stuff like while I learn it, which means stuff gets thrown together and sometimes stuff doesn't work very well. A lot of what I'm going to talk about today is based on material that has been created in the last 3 weeks, so I haven't actually gotten a chance to test implementing yet. And big thanks to everyone in the workshop who has created material that I'm going to shamelessly steal. Oh, is it?
Yeah.
Oh, it's unmuted. Yeah. Oh, I probably do want that. Yeah. All right, if online can hear me okay. I'm the least intelligent speaker here. Don't worry about it. This is entirely me. This is sort of things that have worked for me. You may find better techniques. I didn't know this when I wrote the talk, but Zlatko ran through almost exactly the procedure that I'm going to describe in his talks, and he did a really good job of it. So like what I'm about to describe is going to take a semester, and he did it in 2 hours. And I'm going to be wrong about some things, but Irfan Siddiqui and Vijay really tried their best to teach me back when I was a little baby grad student, so it's really not their fault. All right. If we lived in the world that actually taught people right so that we could really be the best designers and the best researchers and make progress really well, this is what a design education would look like. This is the USC Electrical Engineering Bachelor's in Science program. And this is how you learn to design semiconductor devices. You take all of these courses. I think this is like 2 3/4 full semesters worth of courses. The rest of it is taken up by things like Gen Ed. We unfortunately don't have that. You're lucky if the people that come in to learn to do design have seen the concept of a transmission line before. And so often we're starting from scratch. So this is what we should do. We should really like build up. Functionally, this was my experience. You just, hey, make this. Okay. Hey, it didn't work. I don't know why. Exactly. That's how you get your feet wet, and your head and the inside of your lungs. All right. I teach a course on this at USC. This is part of our master's program. And it's not just on design, it's on quantum devices in general. And this one full semester, it's about 13 weeks. And we start from just about scratch. We assume that people have seen Pauli matrices. And I used to assume more, and now I've stopped doing that because the audience of the course has changed quite a bit. And now we almost a third of the people in there come in with computer science degrees, which means they're really smart and they're really interested in quantum mechanics and in quantum computing, and they have no idea what a capacitor is. And so you really have to like cover everything. And the point of this course was not to like get people to become expert designers at the end of the semester. It was to get them to have a broad enough overview that they could then learn to become expert in some subfield. Get them to the point where they could learn to do a design, or get them to the point where they could learn to do gates, or where they could learn to design a new qubit. So the very first thing that's necessary is just to make sure people have the requisite background. Who here has picked up this book? Who here has regretted picking up this book? This is something I really wish we could get a better version of. There's like one other microwave engineering textbook out there, and it's not nearly as good, but there needs to be a better version of this. This is a useful reference for experts, and it is not a good introductory text. And so this is something that we need a new one of, and that's not something that we should write. We just need to convince the electrical engineers that it's worth doing us this favor. But assuming you're not going to run through all of POSAR, you really have to cover everything, because most people will come in knowing between 50 and 80% of this, but it's going to be a different 50 to 80% for each person, and you don't know what it is ahead of time. And unfortunately, people generally don't want to look like they don't know things. So when they tell you they already know something and you don't need to cover it, that means you only need to cover it once. When they say it's a little unfamiliar, that means you need to cover it 3 times. If they don't tell you anything, they've never seen that concept before in their life. They will, and this is not necessarily people being deceitful. You don't know what you don't know until it comes up. So just cover it. And if it's really just like, boring the hell out of them, they will tell you. All right. So I literally just go back to like intro E&M for high school seniors or first year undergrads, and start there, and just very, very quickly run through everything. You don't need to really cover Maxwell's equations, but you need to know what voltage and current are. You don't need to go through transmission line theory yet, but you need to define the concept of impedance. You don't need to run through the postulates of quantum mechanics, but people should know what bras and kets are and what operators do. And as we'll see, there's one advanced quantum mechanics topic that you are going to have to get to them, but we'll get to that in a second. All right. So this is something I've already done. Next comes what I should do, and I'm going to do this fall when I teach the class again, which is immediately get them hands-on. Because you'll lose them very quickly if you're just drawing lines on a page and writing down equations. They'll say, okay, this is just more theory. It doesn't mean anything. It's just math. Bring a transmon. Bring a $50 little plug-in for your phone or for your computer that has a mediocre microscope, and you can show them the transmon. If you do not have a transmon, please ask any of my students for a broken transmon. We have many. Tell them what's going on. I'm sure most of you have seen many talks where someone comes in and says, here's a transmon. It's an anharmonic oscillator. Here are the levels. Look, it's like a parabola. That's the level. All right, just get to that. Just say, here's what it is. And look, there's your qubit. Because most of the people coming in at least think they know what a qubit is. And it's a surprise to them to hear that it's not actually 2 states. And you can mention, okay, this is going to come up later. But keep it simple for now. All right. Now, start from actual first principles. Pick a circuit quantization technique. It probably doesn't matter that much which one you pick. I'm going to pick the one that I find the best resources on, which is the capacitive spanning tree and node flux technique. And by the best resources, I mean I can email Jens and say, is this right? And he will sometimes say yes, and more often say no, but and then just write down the simplest thing you can, which is an L, a J, and a C with a bias flux, and I didn't draw it here, but a bias charge, a bias voltage. And start from that. That is the simplest possible thing that's going to bring in all the Hamiltonian terms. And write down the Lagrangian. They don't know what a Lagrangian is. Maybe a third of them learned it ever, and they have all forgotten. Between 2006 and 2018, I didn't write down a Lagrangian, so I can't blame them. So go over it quickly, 20 minutes, 15 minutes. What, not why. What, not how. Don't go into Lagrangian mechanics. All right, they don't need to know Lagrangian mechanics. They need to know the Lagrangian exists, and they can just trust you that it works. All right, there's going to be a lot of trust me. in classes like this. Then use the Euler-Lagrange equations and derive the Hamiltonian. Again, they don't need to know why the Euler-Lagrange equations work. They don't need to know what a Poisson bracket is. They don't need to know what a classical Hamiltonian is. All they need to know is that this is the step you have to go to. And then do the quantum Hamiltonian. And it's a good thing Michelle isn't here to yell at me. My procedure is to add hats. Because it is just adding hats as long as you did this first part right. If you did this first part right, you have independent conjugate variables that you're working with, and everything's fine. If you didn't do this first part right, then you can still add hats, but they're just not going to have the right commutation relations. Okay, so now you've got this. What can you do with it? Well, the very first thing is what we always do, which is say EL is going to be 0, because that's going to make things too complicated. Fluxonium is already well beyond what we can do. And you go back to this nice 2007 paper and write down your charge and flux variables in terms of mode operators, in terms of raising and lowering. Not qubit, plus and minus operators, but raising and lowering oscillator operators. Expand out your cosine and use perturbation theory to derive the energy. This is where I say you're going to have to teach one advanced concept. A shocking number of students come into even like graduate level PhD physics never having seen perturbation theory. I don't know why, but like a lot of undergrad quantum mechanics just skips it. They're just like, oh, that's too much work. And I sort of sympathize. This was a meme made by one of my students because I made them solve this exact problem. This is approximately 1/5 of deriving out that transmon Hamiltonian. There's a lot of just with A's. But they need to do it. They need that practice, like because they're not used often to things not commuting. They will just try to commute operators. They don't have like just an immediate sense of this is what a raising operator does, this is what a lowering operator does, even if they're coming in as like physicists. And it's important. And like any other thing in life, the way to get better at it is to repeat it. And like any other cruel professor, the best way to get your students to repeat something is to make them do it 5 million times in one problem. So they do this. It's tedious, but it's straightforward. And you show them the perturbation theory, and you can show them, okay, now you get this anharmonic oscillator. You get this anharmonicity, which to first order in perturbation theory is exactly EC. You can, even if you're really, crazy, go for it and do second order theory. I never do because it's more trouble than it's worth at that point. But you can also bring in here now a voltage drive, and you bring it in as a charge drive. This is something I really want to hit on. Whenever you bring in anything new, do not start from the effective Hamiltonian. This is how you get people who don't know what they're working with. You have to start from the circuit Hamiltonian and then show how that brings the effective one. And in this case, it's really easy. The voltage drive just comes in as basically an oscillatory gate charge. You multiply it out, and you get something that looks like a single charge operator, which looks like A minus A dagger. So these are sort of the steps to run through. And I'm being very hand-wavy about this. I'm not actually showing this because, first of all, this is not the only way to do it. Second of all, I think I've made at least 5 of you do this, so I know you know how to do it. And at least indirectly, a few of you have made me do this because I had to read your papers. So most people here, I think, know how to do this. The question is, how do you teach it? Okay. Like I said, there's going to be people who got into this to prove that BQP equals P. And you need to keep them happy. So you need to bring gates in really soon. All right. Just like you were going to lose people if you only wrote equations, you're also going to lose them if you only show physical devices. So this is the one time where I'll endorse the rotating wave approximation, because without it, everything becomes awful. But write down an oscillatory drive in the lab frame. Use a rotating frame transformation. Show how that gives you an X or a Y, and show how the phase works with this in the rotating frame. Get them this, physical understanding of how a gate works. And if you do this right, you will avert the circumstance that apparently has happened in this field for the last couple of decades that I only found out about a year and a half ago, which is that the people who are writing all the compilers, most notably Qiskit compiler, do not understand how Z-gates are supposed to work. Namely, they understand Z-gates. They didn't understand how Y-gates are supposed to work. This is a small digression, but those of you who work on superconducting hardware know, okay, you want to drive an X gate, you drive an oscillatory tone. You want it to be a Y gate instead, you drive an oscillatory tone with a 90-degree phase shift, right? Not a 180-degree phase shift. But that's what Qiskit does, because X times Z is Y. So rather than shift 90 degrees and drive and rotate your frame of reference 90 degrees, it drives and then rotates the frame of reference 180 degrees. And as long as there's only one block sphere, this is the exact same thing. If you, however, do not have a transmon with infinite T1 and T2, the environment does not notice that you have done a virtual gate. And so if you're trying to do something like dynamical decoupling, it messes you up. So Ariane Vesve he's a postdoc with Daniel Lidar's group, and my postdoc Daria and a couple of people have a paper up on this, which should be coming out any day in PRS Quantum, basically showing like there's a right way to do this and a wrong way to do this. And the right way is at worst exactly as good as the wrong way, and at best way better. So do it the right way. I think most of you already knew this, but people designing the compilers didn't. And it's because when they learned to make these devices, or they learned about these devices, they learned about the effective Hamiltonian. And they learned about it in the rotating frame. All right, now, you're gonna have to get a little more complicated at this point. So you need to introduce a second object. And I would pick one thing that you're gonna talk about and stick with it. So you could take 2 qubits, you could take 1 qubit and 1 resonator. I like to start with 2 qubits rather than a qubit and a resonator because I find readout is going to bring in more complications that you don't want to deal with yet. They come in knowing why the gates should work and what they want. At least they think they do. They often have very little idea about what's actually involved in readout. Signal processing is not something we teach very much. So I like using qubits. You pick 1 2-qubit gate. My favorite is just to use resonant I-swap because it's very, very simple to write down. You could use a cross-resonance gate. That's going to be a bit of a pain. You could use a parametric I-swap. It's also going to be a bit of a pain. You could use one of these CZ gates. Keep it simple. Pick your favorite, but stick with that one. Again, start with the circuit. Start with the circuit Hamiltonian. Stick your 2 qubits together and show that that charge-charge interaction gives you something like a XX interaction or a YY interaction. Do not just write down XX or YY. You have to prove to them that that actually is what happens, because it's not always true. This also allows you to teach them how to calculate things like G, just from capacitances. And this is very helpful because you're still able to do this in a case where the lumped element approximation for your qubits is very good. You're not dealing with like distributed resonators. If you try to do, say, resonator and qubit, you're probably going to want to write down a lumped element model for the resonator. And then the very first resonator you ever show them physically will be a meandering transmission line, and they'll say, what's that? So start small. I like to use perturbation theory for all this stuff because it's a very formulaic approach that they can carry through, and that they can just say like, okay, this is the energy. There's also a very, very simple set of rules for when it fails. If this ratio of the perturbation to the main thing is too big, it fails. If these things are resonant, it fails. Transformations, transforming your Hamiltonian into some new frame and then maybe doing some rotating wave or other approximation, are generally a better and more rigorous way to go about this. if you know what you're doing. But I find a little less obvious to new students when you can and cannot apply, for instance, a particular Schrieffer-Wolff transformation, and when it's going to run you into trouble, or rather, what terms you can throw away and get away with. So I really like to start with perturbation theory. They can learn the transformations later. Okay, so you've shown them the device, you've run through some theory, you've shown them how a single qubit gate works, you've shown them how a 2 qubit gate works. Now it's time to show them how to actually make the device. Okay, so start with something really, really simple. I like a coplanar capacitor, because you can literally just like draw a parallel plate capacitor, show them how field goes. Hopefully they've seen it before, but they might not. Show them, and then unfold it, and then just say like, look, the substrate, it's like a a sponge for field. It's going to take up a lot more of it. You just draw it. You can maybe hint at the concept of these surfaces and interfaces at this point, and just say those will be important later. Give just a tiny bit of hint of the why. Like, why are we making these things big? Why are we making them far apart? Why are the corners rounded? This is why. But don't go into it too much, all right? This is another thing I have noticed during these courses, is that you're going to have to spend a lot of time saying, wait a few weeks. Wait a little while. We'll get to that later. By the way, if you don't have a few weeks, if you're trying to, say, do this in 2 hours like Zlatko did, you have to just skip a lot of this stuff. And that's okay. You just got to pick your spots. All right, so you got these very simple structures. I like to introduce the Josephson junction and just say it's a nonlinear inductor. You know, like we had it sort of at a theory level before. We had the EJ. Show the actual physical structure, say what it is, skip all the superconductivity, skip why it does what it does, mention that it's really, really small and that the geometry is not going to be important for the capacitance and the inductance. All right, just say, this is not going to be part of design right now. This is going to be part of fabrication, and we'll deal with it later. All right, now it's time to give them some rules. Devices look the way they do because we are following some rules, not because we are actually doing an exhaustive search of the entire parameter space and optimizing perfectly. We have heuristics. We want to keep the surfaces and interfaces having as little field as possible. Cool. That's a rule that people can understand. They can internalize it very easily. It might take them a little while to get the intuition for why that makes things big and far apart, but generally, they can remember that. Usually, you want stuff to only couple locally. If you're making planar designs, you don't want super long-range couplings. That's going to be crosstalk. Okay, you can tell people this. Again, they won't necessarily know what that means for how the device needs to look, but they'll know that this is the goal that they're going for. Maintaining a constant impedance. And this one, I do actually like to go in just a little bit more on the why and the how. The why is basically to minimize reflections. You can just show them the formula for reflection. The how, basically just maintain a consistent size. And it's important now to introduce just a little bit of open systems, by which I mean just show them what happens because there is a real 50 ohm impedance outside. And just give them the formulas. Just say like, okay, you can have this Purcell limit, which if you only have, a single mode resonator, gives you this for your filtering. Most of you have probably seen this as G squared over delta squared, not G squared over delta squared plus kappa squared. If I didn't put the kappa in there, Archana Kamal would have been very mad at me. You can generalize this, actually. It's the real part of the admittance at the qubit frequency divided by the effective capacitance at the qubit frequency. And this is sort of like a general formula for an oscillator. Jens, I'm guessing this gets renormalized for a fluxonium because it's not really an oscillator, but for a transmod, it's good enough. Likewise, you can do the same for the resonator line width. And here I like to go the other way. I like to start with the general thing and then introduce a specific geometry, in this case, a capacitively coupled resonator, and say, okay, that gives you this formula. And this sort of tells them, okay, stronger the coupling, the broader the bandwidth. All right, get them actually making a layout. again, we're coming to something that I haven't managed to implement yet, but now there's these really nice notebooks that people have made for this workshop, and so I'm going to just steal them and use them. Keep it simple, though. Keep it very, very simple. This is actually already too complicated of a device. I would not include the feed line. I would have either 2 qubits or 1 qubit and 1 resonator, and leave it at that. But get them laying it out, get them to see just how the parameters look, give them numbers, get them making something that looks like a real device. Don't have them make a transmon that's 10 nanometers across. You can have them make a transmon that's 10 millimeters across. These are the devices that always have the good T1s. You've seen the March meeting. But I really think the closer you can get their designs to ones that are actually going to be in a large scale QPU, the better you'll keep their interest and the better you'll build their intuition. All right, now electromagnetic simulation. Another thing that I had not implemented yet because Pallas was not good enough yet, but now it is. They refined they did a new mesh refinement algorithm. Apparently it works way better now. So I don't have to get everybody an HFSS license. Now I can just have them run Pallas. So again, I would start with the simplest thing you can that's non-trivial. And I would say non-trivial means there has to be 3 different nodes. So in this case, I would pick something like this. I've got a capacitor, a ground plane, and another capacitor plate. And I would end this in a stub, so it's just floating, this bit. And have them run a quick simulation, find the capacitance matrix. Show them what the capacitance matrix means. Show them how that corresponds to the circuit graph. Have them play around with the hyperparameters of the simulation itself. Turn up the initial, turn down the initial seed mesh size, and show them how it gives them a better solution, but it also takes longer in the first few passes. Have them play around with the convergence criteria. Have them crash their computer at least once. I think this is actually really important to show them that this is a very computationally intensive task, and it is more than capable of destroying their laptop. So now that we have Pallas running, cluster is going to come in. If your institution has a spare few $100,000, you can run HFSS on the cluster. Ours apparently does not. All right, so at this point, now I would add in the Josephson junction, show them how to do that in the simulation, which Murat's going to show later, and run an eigenmodal simulation and show that you actually get a resonant frequency, and have them compare with what they would calculate from their electrostatic simulation, from their capacitance matrix, with just writing down the inductance of the Josephson junction. Do not do EPR yet. Okay, EPR is fantastic. It really gets you everything you need. They will not understand it correctly, and they will not understand how to know when it's failing. EPR, the biggest danger is that it's so good at giving you everything that you're really tempted to just say, simulation, EPR analysis, done, without actually understanding any of the steps in between. And it's not as bad as it used to be, but there are still assumptions built into a lot of the helper functions in the PyEPR code that if you don't know what you're doing, you wouldn't know that those assumptions are there. For instance, at least until recently, there was a Purcell limit calculation that assumed a very particular type of Purcell filter from some IBM paper in 2011. Not even like a certain geometry, but actually a particular filter line width. And it was just built into the back end of the code. So if you just type it in, you're like, okay, my Purcell limit is this. No, that's not your Purcell limit. It has nothing to do with it. So do not give them too many tools, all right? Make them struggle with the basic theory to start. All right, now, when doing this, start with a real device. Start with one that you actually have data for so that they can compare and show them that it's wrong, show them how turning up the accuracy makes it better, 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 to some limit. like any millennial, I think only in terms of memes and quotes. This is one that comes to mind a lot. This data down here is from Shanto's squads paper. This is 6 qubits and 6 resonators on a chip, simulated values of the anharmonicity and the qubit resonator coupling, the resonator frequency and the resonator line width, compared to the measured values. And, you know, they're close, but they're not the same. The resonator frequency, you can see there's very clearly a systematic error here. We know exactly what that is. That was actually just because in the simulation, we didn't include the airbridge crossovers because MIT says they're secret. And we want to keep them happy because they make us good devices. It doesn't really look like it on this scale, but actually the accuracy for the line width is pretty terrible. The accuracy for everything else is not bad. You know, we've got it within 5%. And it's really important to know whether that's your fault as someone who's running simulations or whether Bigfoot is blurred. So you have to show them what is and is not reasonable in terms of matching simulation and experiment. This is, I think, a very enlightening exercise to go through. Most microwave components will not say that they have better than minus 20 dB return loss. The best they'll usually claim is minus 15. But let's say you've got one that's minus 20 everywhere. You've done an amazing job making your microwave circuit board launch. It is, you know, minus 20 dB. That means 1/10 of the voltage gets reflected, which means you have about a 20% mismatch in the impedance, which also means you have about a 20% possible variation in the line width of any resonator coupled to that. Purely because you didn't do a perfect job of like soldering your connector to your board. That has nothing to do with your design. Now, okay, people are getting better at making these boards. People are getting better at making these bonds. You know, maybe 20 dB will start to be not so unreasonable of a standard to expect. But in my group, I think we're pretty happy if we're flatter than minus 10 dB across the whole range. So we don't want to expect more than, say, 30% variability in the resonator line width. That's, if we get within 30%, we're calling it good. On the other hand, the resonator frequency is quite insensitive to this. And so you should be able to get that to within a couple percent easily, maybe a few tenths of a percent. Qubit frequency, I say 1 to 2%. It really depends on how good your fab of your junctions is. Because if your junction EJ is just different than you wanted, that's not a design problem per se. That's probably a fabrication problem. And it will change the frequency. The charging energy of the qubit, you should be able to get that really good. Because that's usually a pretty small structure, just a capacitance simulation. You can usually turn those simulations up really, really high accuracy without taking too long. All right, anharmonicity is not the same as EC. Not just because, you know, anharmonicity equals EC is an approximation to first order perturbation theory, but also because it turns out that our Josephson junctions aren't perfect sinusoidal junctions. And our capacitors aren't zero-size elements with no inductance. And it's not totally clear to what level that contributes. There's now these papers showing the presence of these higher Josephson harmonics, that there's not just a cosine phi dependence, but also a cosine 2 phi, 3 phi, 4 phi. And that changes the anharmonicity as a function of EC. So in my group, when we say, okay, we're going to measure this design and see what it actually produced, we just measure the anharmonicity and we call it EC. But really what we should be doing is measuring like the next 5 levels up and doing some fit on this. So if you want better than a few tenths of a percent accuracy, this is probably what you need to do. All right, so this is accepting that there's just going to be some things that you'll never hit accurately. On the other hand, you should make sure that the accuracy isn't you doing your math wrong. All right, who here has seen this expression for the Lamb shift or the punch-out shift? G squared over delta. Okay. That's wrong. It's G squared over delta minus G squared over sigma, where sigma is the sum frequency of the qubit in resonator. And this is because g squared over delta is what you get if you take the rotating wave approximation. If you take a charge-charge interaction and throw away the energy non-conserving terms. But you shouldn't do that. All right, who here has seen this expression for the dispersive shift, 2g squared over delta? By the way, that factor of 2, I'm going to start insisting on that now. Dispersive shift is the full shift in the resonator frequency when it goes from qubit ground state to qubit excited state. It's purely a convention, but we have to pick one. Sorry. That's also wrong, and I think I would say most sources will tell you that's wrong for a transmon. They'll say it's actually this. It's 2g squared alpha over delta times delta minus alpha. But this is taking into account the fact that the transmon is not a qubit. It has higher levels. And those higher levels with anharmonicity alpha are going to reduce the dispersive shift by basically pushing the levels the other way. That is also wrong. This is what you get with the full Hamiltonian, including the rotating wave approximation. Now, in this case, sorry, not taking the rotating wave approximation. This term doesn't contribute nearly as much as this one here, because you can see this is 1 over sigma, this is 1 over sigma squared. And sigma is generally larger than delta. Yeah. I use the convention that the 1-2 frequency is omega plus alpha. So a transmon has alpha as a negative number. Yeah, that's a good question. Like, we should settle on a sign convention. We should settle on a definition of chi. We should settle on a definition of g, whether these factors of 2 are there. We should stop abusing the letter delta. There is a question online which I can't quite see, but at what point is it appropriate to introduce nuance or hint at broader concepts, if it even is, such as phantoresonances, overcoupled, undercoupled? Not yet. I will get to it. Anyway, these are the correct assumptions, correct expressions to second order in perturbation theory. They're still not exact, of course, but they're generally good enough. And I really do need to insist on them because we were pulling our hair out for several weeks working with the ones we'd seen in literature until we went and actually re-derived them. And let's say you have a pretty reasonable scenario. Let's say you have a qubit at 7.5 gigahertz, 3.5 gigahertz with a readout resonator at 7.5. It's a transmon with minus 150 megahertz anharmonicity. And you're trying to compare from EPR analysis, your dispersive shift chi, to your measured punch-out shift, chi-L, the lamb shift. That ratio changes by a factor of 2, depending on whether you take the rotating wave approximation or not. But it's not small. That's enough to make you think that something's horribly wrong in your simulations, and it's not. Something's horribly wrong with your taking of approximations. So be careful about this stuff. Basically, don't take the approximation, go and calculate the answer, take the approximation, make sure it doesn't matter, then you can use it. This is not a particularly helpful way to train students a simple thing, so you have to do it for them and tell them when it's not, is and is not okay. All right, now you can start to introduce some complication. So now you need to pick one thing. Could be 2 qubit gates, could be 2 Noble couplers, could be Purcell filters, could be these like, non-idealities of the resonant line shape of resonator. And really go into detail on that. Again, start with the circuit graph, start from first principles. If you're dealing with some sort of classical microwave resonance, start with calculating the impedance. And do everything you can, everything you have resources for, everything you have time for. Start to introduce non-idealities. Say they're looking at 2 qubits. We'll say, okay, give them drive lines. Let's look at the crosstalk. Let's look at the ZZ crosstalk that's induced. Show them how this starts to come in. You cannot and should not try to cover everything. Pick 1 or 2 non-idealities and show them how they come up, and then maybe list a bunch of other ones that they should probably look for. All right, they need to learn how to learn. You're not going to be able to teach them everything. It's at this point where I would introduce the other simulation analysis techniques. things like EPR analysis, things like black box quantization. And you can go into detail on them if you want, if that's the thing you want to spend your time on. Or you can just say, okay, read these resources. Again, don't do it yet. Like, don't do it before this point. Because if you do, they'll look at EPR and they say, well, that gives me all the answers. I'll just use that from now on. And if they don't know what's going on in the back end, they'll do it wrong. All right, if you have time at this point in a one semester class, you guys are flying. If this is a lab, not a class, like just throw them in the clean room at this point. Like, you know, they're ready to start making things. This is way more education than I ever got. But if you're still in a class and you still have some time, really, really dig down on like one thing. And I prefer Purcell filtering at this point, because I think the one thing that we really don't get enough of is classical microwave engineering. And Purcell filtering is really, really addressed best with classical microwave techniques, just looking at impedances and admittances. And so you can just dig down into that and show them how a bunch of different Purcell filters work, and show them all the counterintuitive results you get from Purcell filters, like how sticking a Purcell filter in front of something can make the resonator suddenly extremely broadband, that kind of thing. Alternately, you could just sort of show them what happens when design goes wrong. So my student Vivek is in the audience here. This is what he eventually made and got a nice paper out of. This is the first thing that I told a former student to make for the same device, and these are to scale. These are tunable couplers. I think you can kind of look at this and guess that that's a way bigger capacitance up here than that over there. It's important to show them what goes wrong and why. Can anyone guess why we did this one so wrong? What was wrong with our simulations? It was not the factor of 2. No, so this was actually not a rotating wave approximation thing, but it is something else I've been harping. We naively used PyEPR without looking into the back end. Everything I harp on is a mistake that I've made, and I don't want other people to repeat. Yeah, we just had a bad simulation and just ran PyEPR on it with the wrong backend stuff, and it gave us an answer. We said, cool, that's the right answer, we'll go. And it just wasn't what the thing was going to do ever. So, give them some cautionary tales. All right, there's one other thing I want to cover, which is that we need a textbook. That's it. No, okay. We need to think about what kind of textbook. Do we want actually something that's covering all of sort of CQED, something kind of big that's going to cover not just, say, how to design devices, but how to run them, how to measure them, how, everything. This is, I think, the book that Dan Sank is talking about writing, that I think I've sort of committed to help with, and I think probably you all have too by this point. But we could also just like narrow down and write smaller ones. And those would have to be interdependent. You'd have to sort of assume some background knowledge from some of the other ones. I think probably the one big book is going to be less of a logistical challenge, so we'll probably go that way. But we need to figure out who we're targeting. I teach my course getting a huge, broad range of students, and I do not think we should write a textbook for that. I think we should assume that by the time they get to the circuit QED textbook, they have learned quantum mechanics. They have learned basic E&M. If they haven't gotten those yet, they can go read an E&M textbook or a quantum mechanics textbook. There's hundreds of them. Let's not reinvent that wheel. That wheel has been perfected. There's also just this question of what do we include? How close to up to date do we want to be? There's this stuff on symplectic geometry for circuit quantization that can handle things like when you have a phase slip and a Josephson junction in the same circuit, so you have nonlinearity in both your variables, or when you have non-reciprocal elements, so you can't write a Lagrangian because it matters which direction you define your variable going. Probably not worth getting into. Someone has invented a qubit in the last 6 months. I haven't heard of it yet, but I'm sure it's happened. And do we want to cover that? Do we want to cover the latest simulation techniques? My sense is no. because we're never going to be able to keep up. We're never going to be able to write a book that trains people to just go into the lab and do the cutting edge research. That doesn't exist for any other things we do in lab. The best we can hope for is to get people to the level where they can read papers and learn. And so I think that's what we should shoot towards, the back. All right, that's all I have. Thank you for listening to me rant. And if you have any questions, I'll take them. Yeah.
Sets of qubits, array, etc. But somewhat of a QDW, you have some low power.
Yeah, so, I mean, one thing that's crucial when you have like a larger array is just thinking about what's your JJ repeatability. You know, how well can I make the exact same Josephson junction twice? And that's where this sort of 1 to 2% number is coming out. You know, because that's about half the variance in the junctions that we can sort of semi-reliably hit, and half the variance in the junction EJ, it gives you the variance in the frequency. Maybe you've got a way better fab, in which case you should be able to turn that down, at least in terms of repeatability, you know, precision, if not accuracy. Likewise, EC, I think you can get that very, very, very repeatably in terms of precision. You might miss a little bit, but I bet you can make the exact same capacitor over and over and over. Because at that point, the repeatability is down to like how well you can draw the exact same shape. And if your shape it has an area of hundreds of square microns, your fabrication variability might be, you know, square nanometers-ish. So it's really not going to matter. You should be able to hit that exactly. Likewise, resonator frequency, you should be able to hit that really, really well, but you might have biases. That's the thing. You're gonna be repeatable, but not accurate if you're not careful, because it's hard to correctly include things like crossover junction, or air bridge crossovers, to really account for them correctly, to really account for the effects of flip chip. I'm anxious to hear what Ben has to say about that later. But it should be repeatable. And so this is good because usually you're not trying to exactly hit a certain frequency with your resonators. You're trying to hit a certain frequency relation between all your resonators. You're trying to space them closely and get them all within the Purcell bandwidth or something. And that should be quite doable. Line width, that's, if you get 30%, call it good. You're already ahead of the game. And that's variability across a chip. That's not accuracy, that's precision. You're gonna have just scatter of this because it matters exactly how far away you are from some bad impedance match. And that's not gonna be something that you have great control of. Even if you've done everything perfect, last time someone closed up the fridge, they accidentally kinked a wire and the cable, the connector on that SMA went from being minus 25 dB to minus 15. Congratulations, your impedance just changed by 30%. Like, there's nothing you can do. Anharmonicity, I don't know. I think actually if anyone is interested to just do a broad survey with a lot of spectroscopy, this would be a good topic. And I think it's probably not that difficult of an experiment to do, but might require a lot of fridge time. So if anyone has fridge time to spare and lots of single qubits, go just measure all their spectroscopy and then do some careful simulations. I think you'd want a range. I think you'd want a very broad range, and you need to do spectroscopy up to a very high energy level. At least I would say the 4th or the 5th energy level. Yeah.
So like it's usable about like 61. You mean not like 61 ohms like broadband across like 4 to 8, whatever you're operating in? How much?
Well, I would say that if you have a 50 ohm running into a 61 ohm, you'll get minus 20 dB return loss. If you're some number of wavelengths away, depending on exactly how many wavelengths away you are, the impedance you see will range anywhere from 60 to like 40. And that's why you get this variability. I think there were some questions online. One was just how, oh, sorry, I missed these. These were kind of a ways back. How much of fabrication should you cover? I would say only enough to say what's reasonable to hit in terms of repeatability. You can go into fab as a special topic, but I think designers only need to know it in the sense of like what is and is not possible. And maybe at the end, just talk briefly about how to account for fab bias, how to account for the fact that when you draw a GDS file, you have to account for like the actual features that get created might be a little bigger or a little smaller. There was one about the slide between the comparison between simulation and experiment. Wouldn't it be better to have students exactly match a previous simulation and then follow up by showing that these can be deviations from measurements and quantifying those? Leading off with you're going to be off anyway devalues the role of design and simulation. Yeah, this is true. And I did not say this as it was actually the plan, was to have a really good simulation run on like a mainframe or on a cluster that we can say this is correct, but also wrong, because that's not what the real device does. And say, okay, this is the best we can get with simulation. See if you can get to that. Also, here's how accurate that's going to be. And is there any other? Yeah, one thing to dig into is all the old microwave papers from the 60s on filter techniques, CPW geometries, etc. Yes, someone please dig into those for me. Right, any other questions? And I will stop standing between you and the food.